Hey everyone, welcome to the last lecture. I can't believe we made it on 12.3, the regression equation. So the regression equation is also sometimes referred to as the line of best fit. And in particular, the type of regression that we're talking about here is linear regression. So recall that when we were talking about scatter plots and correlation, we were saying like, hey, can I draw a line through this data? Let's kind of go back and look at that real quick. Can I draw a line through this data? Is that going to help me kind of figure out what the trend is? And so now we're actually going to do that. We're going to see if we can get a line through this data that tells us something useful, helps us model, helps us predict. So whenever we're doing this method, the first thing we have to do is we have to make sure that the correlation coefficient R is statistically significant, meaning that we have to have a p-value for our hypothesis test for R that allows us to reject the null hypothesis. So after we run a hypothesis test on R, and if our p-value is at least as small as alpha and we get to reject the null hypothesis, then we can proceed with the regression equation that we see here. So we've got y hat, we've got bar, we've got capitals, we've got lower cases. If you made it this far, I'm super impressed. This is the last hat, I promise. So y hat is going to be the predicted value of y for a given input of data x. So remember that we are trying to create a line through the data so that if I said, well, what if x was 10? Based on this trend, what do you think y should be? That answer, that's y hat. It's like a predicted value of what y should be. It's not the true value, there's some variation there, but it should be relatively close depending on how good my correlation is. And then we see that it's A plus BX. And so we have these formulas for A and we have these formulas for BX. So B is simply the correlation coefficient from the sample times the sample standard deviation for Y divided by the sample standard deviation for X. And then to compute A, it's going to be the sample mean from Y minus B times the sample mean from X. And Excel is going to crunch it out for you, so we don't have to worry too much, but we should know where these things are coming from. So it's all coming from sample data. So remember, R is our sample correlation, SY, SX, those are our sample standard deviations, X bar, Y bar, those are our sample means. Let's look at an example to see how this is going to work. So let's use a linear regression on our calculator, which for us is Excel, to find the equation of the linear function that best fits this data. So without checking, let's put our data in here and see what we get for our line, and then we'll go back and we'll check to see if the correlation is statistically significant. So once we've inputted our data into Excel, it's going to compute our correlation coefficient. It's going to compute our sample means for X and Y. It's going to compute our sample standard deviations for X and Y. Not that we need those, but just to show that they're computed. And then it's going to give us A and B. So when we are asked to find the equation, it's up to us to take these coefficients A and B and put them into a y equals mx plus b form. But let's just check to make sure, and I have a sneaking suspicion that will be just fine, but let's make sure that our test for correlation is going to work. So I'm going to go ahead and paste these here. So our correlation coefficient was here, which was E20, E16. And our sample size was 6. Right, so again, we can see our p-value 1.9 e to the 0.006. That's tiny, that's 0.000006. And let's go grab our other stuff. So we're seeing here that P equals 0.1, 2, 3, 4, 5, which is, there's no alpha that's going to be that small. So, right, so remember the common values for alpha, 0.01, 0.05, and 0.10. So this beats all of them by a lot. And so here we will reject the null hypothesis. Right, so we're rejecting the claim that rho equals 0. So we're rejecting the claim that there's no correlation between the populations. Okay, so having that done, now we can actually use our 0.99887 in our line of best fit because it is statistically significant. And what we get here is our regression equation, and it spits out our A and our B. So what we're going to have is that y equals 56 point, let's say I'm just rounding to 2 decimal places. And that's it. That's your regression equation. So this next equation, or sorry, this next example is going to be pretty similar. We've got a list of data. We are asked to verify that correlation is significant at alpha equals 0.05. And then if the correlation is significant, we're going to use our line of best fit to make some predictions about the explanatory variable that will give you a response variable of 110.8. So let's take a break so I can put those into Excel, and I'll be right back. All right, so I copied and pasted my data into Excel. I've taken my correlation coefficient as well as my sample size and put them into my hypothesis test calculator at the top. And then I want to verify that the correlation is significant at alpha equals 0.5. So I'm just going to put 0.05 here. And so my p-value is tiny. So my p-value is essentially 0. So let's kind of, I'm going to plug into this here. Right, so this is really, really small. All right, so now we're on to the part where, since the correlation is significant, predict what value on average for the explanatory variable x will give you a value of 110.8 in the response variable y. So this is saying when y is 110.8, what will x be? So the way that we're going to do that is we're going to go over to our prediction box. So we're given a y value of 110.8. And when I put in a y value, it's going to spit out an x value. So here we see that the answer to this question is x would be or should be 55.87, etc. So your answer is just right here. Right, so what is the predicted explanatory value? That's actually the same question. So the predicted explanatory value is just the predicted X value. It's 55.87, et cetera. So let's do one more example here with some data. The table below shows the number of state registered automatic weapons and the murder rate for several Northwestern states, where X is thousands of automatic weapons and Y is murders per 100,000 residents. So we want to use our calculator, our Excel, to determine the equation of the regression line and write it in the y equals ax plus b form. And that really should be a plus bx. So let's start by running our hypothesis test to make sure that R is statistically significant. And let's see what we get. So when I put my data in, I get a correlation coefficient of 0.99866. I mean, that's very strong, but my sample size isn't that big. It's only 8. So I run my hypothesis test and I still have a p-value that's incredibly small, right? So our p-value is essentially 0. So that's going to beat out any possible value that we could get for alpha. All right, so since the p-value is so small, it's gonna be less than or equal to alpha for any standard significance level. And so we're gonna go ahead and say that there is significant correlation. And now we're gonna move to our calculator to compute the line of best fit, or the regression line. All right, so I'm gonna copy my data from here. And I'm going to paste it here, get rid of all this junk. So now this is going to give me my information that I need for my regression equation. So I can write that y hat equals, let's just do 2 decimal places, 3.90 plus 0.85x. And then according to this model, how many murders per 100,000 residents can be expected in a state with 7.3 thousand automatic weapons? So was the number of automatic weapons, was that an X value or a Y value? We go back to our problem. X is the number of automatic weapons. So I'm going to use X equals 7.3, and I want to figure out what my Y is. All right, so when X is 7.3, we see that Y is 10.122 roughly. So if I can put this in here, so we would predict 10.12 murders per 100,000 residents in a state with 7.3 thousand automatic weapons. And then in the next one, it says, according to this model, how many murders per 100,000 residents can be expected in a state with 8.3 thousand automatic weapons? And that's very much the same thing. Let's just change this to 8.3. And we would expect 10.97 as our answer.